see. So you guys can see my screen now. And here's the notes. And here we are. Okay. Good. Very good. So let's get the ball rolling. So as you said, Maddie, is the last day, last lecture of the school after the final lecture by the closing lecture of the school by Karum and nice lectures by Lars. It's very late there, and I don't know how you're feeling, but if I was you, I would be feeling very tired. So I'm gonna keep a light lecture today. Okay, I'm gonna finish. I'm gonna wrap up the coordination story that I was telling you about yesterday quickly. Just gonna give you the punchline, and then I'm gonna move to one final, I think, very exciting conjecture that I've been working on with Guru and other friends. This festina lente bounded. Oh, oops, there we go. So it's a bit more. Come on. There we go. It's a bit more speculative than the other stuff that I've been discussing in the lectures, but the consequences are more interesting. Okay, so let me then quickly finish what I was the story I want to tell you yesterday. So yesterday we spent a lot of time talking about topology change, in quantum gravity, and this so-called, which led to the covariance conjecture, which says that the covariance groups of quantum gravity must be trivial. It's a version of the no global symmetries conjecture. Okay, fine, that's great. Why did I spend so much time on this one? Well, I spent so much time because it has been at the core of, I would say, one of the most precise tests of Swampland principles. And the one case that I know of where Swampland actually made a prediction for string theory, and then this prediction was later verified in string theory. If you remember, a couple of days ago, I was telling you how for 10D n=1 theories, we have string universality. Meaning everything that you can get from Swampland, you have these 4 gauge groups. And then we were able to see how these two are in the Swampland, and these two are actually realized in string theory. So everything is true. So what I'm going to be telling you very quickly now, okay, I'm going to be a bit schematic. And there's all of these, for instance, you can find in a series of recent papers by myself, Kurumbafa, Yuta Hamada, Alec Pedroya. So even starting in 2020, 2021, these are all pandemic papers. And I don't think there's anything on this topic in 2022. Anyway. Okay, so let me tell you what is the story here. So we're going to try to achieve the same thing as string universality in 9D, 8D string theories. Okay, so we're going now. So if you remember, I told you the other day that any string theory, any quantum, any supergravity, any supergravity with 16 supercharges, which is minimal SUSY in 8D and 9D, has one gravity multiplet plus a number R of vector multiplets. Okay. The content of the vector multiplet is a bit different in 8 and 9 dimensions. So there's a vector, a gaugino, there's also a scalar transforming in the same representation. Okay. But other than that, it's the same. So the question, so if you want to write down a supergravity Lagrangian with in 8D or 9 dimensions, you just need to tell me, to write the Lagrangian, you just need to tell me at the generic, what we call generic model space, you just need to specify an integer, R, the number of vector multiplets that we need to put, okay? So I'm gonna draw for you a table which reflected the knowledge of this thing before we wrote this paper. So for any dimension, okay, I'm gonna draw dimension 9, 8, and 7, and then I'm gonna draw here the possible values of the rank. So of course I need to say 1, 2, 3, 4, 5, 6, 7, 8. So let me just write dots here, and I'm gonna make dots until 17. And then in 8 dimensions, I'm gonna do the same. So I'm gonna copy this and then paste it. Come on. Oh, sorry. And actually, for some reason, I wrote a 9 again, but I meant 7, of course. Okay, so here, I'm gonna draw dots until 18. Okay, so let me actually, 8. Oh, come on. 8, 9. And then I'm gonna say 8, 9, 10, and then to 18. And then here, I'm gonna, yeah, so I'm gonna actually copy this, paste the same thing. If I can. And then, yeah, this time I'm gonna erase to 11, 8, 9, 10, 11, all the way to 19. Why am I doing this? Well, we know from Swampland principles, basically from a version of the distance conjecture, that in 9 dimensions, the rank is upperbounded by 17, in 8 dimensions by 18, and in 7 dimensions by 19. Okay, this is just something that we know. And now I'm gonna mark in green, okay, in this table, the ranks of theories, the values of the rank for which we have a known string construction. Okay, so let me just do that. So we have rank 1 in 9 dimensions of string construction, also rank 2, rank 3. Then we also have a construction in rank 9, and then another rank 17. And here we have constructions in rank 2, rank 10, and rank 18. And for 7 dimensions, we have ranks 1, 3, 5, 7, 11, and 19. Okay, so green means we have explicit string construction, meaning we can find the string theory compactification that the low energies gives this kind of thing. And now I'm going to color in red theories which are inconsistent. Okay, theories which we know have an inconsistency. In this case, what is called a global gravitational anomaly. So in the same way that in 10 dimensions, there's only 4 groups that are consistent, in 9 dimensions and 8 dimensions, not every value of the rank is consistent. And actually you get like a checkerboard pattern of things that are forbidden like this. So it's odd, even ranks in 9 dimensions, odd ranks in 8 dimensions, etc. Okay, so those we know they don't exist, but anything else we don't know if it exists or not. Okay, or we didn't know before we had this paper. So with this kind of principles, using the covariance conjecture, one can put additional bounds on this value of the rank. Okay, so how do we do it? Well, it turns out that all these theories have a parity symmetry. Somebody was asking the first day if the no global symmetry conjecture applies to space-time symmetries like parity. Well, here's an example. These theories have a gauge parity symmetry, so it's an exact symmetry. Okay, and it's a parity symmetry of a particular kind. Supersymmetry means that the parity symmetry equals to -1 to the f. What that means is that on bosons, it squares to +1, but in fermions, for fermions, it squares to -1. Okay, This follows from the supersymmetry algebra. Now, this parity symmetry, so what that means is that when I consider these theories and I consider them on an arbitrary manifold with holes or whatever, this manifold must have what is called a pin minus structure. That just means that there must be a way to define fermions in this manifold, which are consistent with this structure. Okay, that's all it means. It's just the mathematical way, the mathematical way we encode the fact that that you have this symmetry structure in the theory. Okay. Any questions so far about the supergravity theories? So this is the picture. This is how the landscape here looks like. It's just defined by a number, and the job of a Swamplander person is to tell you which values are okay and which values are not. Okay.
So we added matter multiplets just because of simplicity, right?
No. So there's right. So there's a gravity multiplet. So the only thing that you can do with this supersymmetry, you can have the gravity multiplet and vector multiplets, and you cannot use any chiral multiplet or anything. It's just vector multiplets that is there, and we added them because this is the only other possibility, and this is what you realize in string compactifications. So from supergravity, there's no, because there's so much supersymmetry, there are no more multiplets. It's very simple. It's very simple theory in a sense. So you have these guys. Any other questions, please? Okay, so we have these guys, and we need to have this P minus structure. And I told you yesterday that the covariant groups of a theory depend on their structure. So in this case, we need something called the P minus covariant groups, which have been computed by, is there a question? By Reza, please.
Yeah, excuse me. Aren't there form fields in these green marked theories?
Are there what? Sorry, what kind of fields?
Aren't there form fields?
Differential form fields.
Differential P forms.
Yeah.
The green marked theories. Aren't there?
Yeah. So what happens is so as we discussed the other day, there's a two form, okay, in the gravity multiplet. So I have the gravity multiplet. The gravity multiplet has a B mu nu field here, okay, which of course has a dual, right? So for instance, in 9 dimensions, the field strength is achieved at 3 form, H mu nu, and so its dual is gonna be a 5 form. So there's gonna be a dual potential, which is so it's a 6 form. There's a dual potential which is gonna be a 5 form. Okay, so those exist, but those are the only two that exist. You might be thinking that when you compactify, for instance, string theory in 10 dimensions has many more Ramon fields, and that is true. The way you construct these compactifications, which have reduced supersymmetry, so type 2B string theory in 10 dimensions has 32 supercharges. These are theories with 16 supercharges. So you need to compactify them on manifolds with holonomies of particular types, and those holonomies kill some of the Ramon forms and leave just a few of them surviving, which are the ones that are in the multiplets. Did I answer your question?
Thank you. Yes.
Thank you. Okay, good. So we have this guy, and mathematicians have computed all the covariant groups. There's one that we're interested in, which is this omega 2 pin 2, which is a Z8, and is generated by RP2. What is RP2? RP2 is just a sphere, a two-sphere quotiented by antipodal mapping. So you take a sphere and identify antipodal points on it. Okay. So what that means is that these theories you can compactify. Sorry, that was not a great drawing for RP2 because it's a simple manifold. So these theories you can actually compactify on RP2, and because this thing is that has a non-trivial covariant group, there's going to be a global symmetry. So the covariant conjecture predicts defects, okay, that kill this symmetry, predicts that this thing is actually a boundary using singular geometries. The singular geometry for which, so what is the singular geometry which has RP2 as boundary? It's very simple. It's just R3 mod Z2, where the Z2 sends x, y, and z to minus x, y, and z. Minus x minus y minus z. So just take R3, reflect all coordinates around the origin, okay, quotient by that, and that is giving you a configuration like this. The RP2 that you're getting here is obtained by putting on this S3, you embed an S2 as the sphere's radius 1. And then this action here becomes antipolar mapping when restricted to the S2. So it's producing the RP2. Okay. This thing that I described here is not a manifold. It's an orbifold. It's a singular orbifold because at the origin the action is free. Sorry, it's not free. A supergravity person, if I go with this supergravity theory and I tell a supergravity person, this is an allowed background of the theory, they're gonna be, well, I don't know, because this is a singularity, it has high curvature. It is only because of the covert-descent conjecture and the Swampland principle that we know that we can compactify on these things. So if you can have this thing, here's what the trick comes. If you have this thing, you can actually make a compactification which involves 8 of the singularities. So for instance, you can take T3 mod Z2. T3 mod Z2 is a 3 torus. So just basically take this action and make all coordinates X, Y, and Z periodic. And that's a compact geometry. This compact geometry it's kind of like a cube where the corners locally, the 8 corners here, look locally, not like normal corners in a cube, but like copies of this guy. Okay. You can, and the trick, the basic trick that one uses is because of covert-descent conjecture, because of Swampland, we know we can compactify in this. So we can take the 9D n equals 1 theory, for instance, and compactify on T3 mod C2, on this guy. Okay. When we compactify on this guy actually preserves half the supersymmetries. So the compactification is a 6D 1,0 theory, which has very powerful anomaly constraints. Okay. 6D supergravities have very powerful anomaly constraints. And it turns out, I will skip the details because I don't think it's the point and it's late and so on and so forth. You can find the details in our paper. It turns out that the imposing, if you remember from the other day, I explained that anomalies for gauge symmetries, in particular gravitational anomalies, must cancel. Okay, this imposing this condition comes, actually the anomaly of this theory depends on the rank you started with. This discussion we did was very general, so it's valid for any value of R, but the result, the anomaly, depends on R. So it doesn't cancel for a general R, and the condition that the anomalies vanish is that the rank is congruent to 1 modulo 8. Okay? What that means is that the only allowed values of the rank according to the Swampland constraint, which we got just from covert-descent without ever mentioning string theory, in 9 dimensions are 1 plus 8 equals 9, 1 plus 16 equals 17. This is in 9 dimensions condition. And in 8 dimensions, what you get if you repeat the argument is that the rank is 2 modulo 8. Okay, these are the conditions that come from covert-descent conjecture. So if we go back to the table here, we see that what this condition is doing is allowing us to color in red this entry and this and this and this and this and this. All of these theories are being ruled out, and all of these theories are also ruled out. To the point that what you can find from Swampland principles, exactly, just like in 10 dimensions, exactly matches what you get in string theory. You get string universality. Making this argument in 7 dimensions leads to a modulo 2 condition. So for instance, it tells you a lot of things. It tells you all of these are not allowed. But for instance, it doesn't completely solve the question because, for instance, this one, it's possible, and there's also some yellow and some red. So we haven't achieved string universality in 7 dimensions, but we have achieved it in 8 and 9 dimensions. Okay. This is what I wanted. This is the basic lesson that I wanted to convey to you. And I think it's also an interesting lesson because it's very, this is something that if you're really interested, there's a lot of things to explore here. This is something one can work on. The idea is that covariisms, when combined with anomalies, equals very powerful constraints. And just to finish the story, and then I'll take questions about it. There's I simplify things a little bit here. I told you that the theory only depends on the number of vector multiplets, so that's the rank of the gauge group. But at special points in moduli space, you can have enhanced non-abelian symmetries. And the covariism conjecture with the same principles, covariism plus anomalies, also constrains, just like in 10 dimensions, the gauge groups you can get. And in particular, there's one prediction that we made from these principles, which is that a factor like SPK mod Z2, where K is 1, 2, or 4 mod 8, we said that this thing is in the swamp. And at the time when we wrote this paper, people have not computed all the possible non-abelian gauge groups in 8 and 9 dimensions. They did it after the paper, and they checked, and the results that they got from string theory exactly matches what you predict from Swampland. So it's really very predictive principle. Okay. So this is predictive and strong constraint. Of course, it has one very, very big downside. So I'm gonna put in, I'm gonna make very clear, one big downside, which is we use SUSY and high dimensions. The fact that we're in 10 and 7 dimensions a lot. So it makes it difficult to connect to the real world. So now I'm going to change the gears and explain how to connect very strongly from a different Swampland principle to the real world. Okay, but before I do that, let me perhaps take any questions you might have about this story about anomalies and covariisms. So I wanted to give you a very strong application of the covariism conjecture. I think that the covariism conjecture is in a sense a version of no global symmetries, and this is the strongest application one has for basically any Swampland constraint. You could use it even to, we used to, it was precise enough that we could make predictions about what you will find in string theory that when later verified. Any questions about this?
So is there a technical barrier that we cannot do in lower dimensions? I mean, super SUSY is not that constraining, I assume, right?
That's right. That's right. So the point is, so the difficulty is twofold. First of all, SUSY is not that constraining, and second, the higher dimension you are, the more powerful anomalies are. When you're in lower dimensions, anomalies become less powerful, and the two things conspire to make it harder. So for instance, one thing that we are doing, we're thinking about these principles and apply them directly to the standard model. And it's difficult. We haven't managed, we've managed to recover some of the things that we know, but it's difficult to make stronger constraints. In 6D theory, for instance, one other setup where you can still apply these principles in 6D compactifications, and they map to properties of F theory fibrations. So it's kind of secretly, these techniques in 6 dimensions secretly know about the theory a little bit, but it's not a very strong constraint. And I think but I think it's really very interesting that you can combine Swampland principles and make them this powerful. And I really hope that by thinking about it in the right way, we can make them strong also in lower dimensions. This is one of the things, for instance, that I wanted to show you also some of the recent developments that I'm very excited about, also to encourage people to become interested in them as well and work on them. This is an open problem, guys. How to make this better is an open problem, and an interesting open problem one could work on.
So I assume if we compactify a manifold with trivial holonomy, then the SUSY part is untouched. So the only remaining thing is the anomaly constraints.
You're completely right. You're complete. So for instance, that is the reason. Already you see here that in 7 dimensions, for instance, in this case, we are not that strong, and it's precisely because of that. The supersymmetry is the same, but the anomaly is much weaker. It's precisely because of that. For instance, for 7 dimensions, we are now analyzing from a slightly different Swampland principle, and we seem to be able to also get these cases. So there's a lot of progress that one can make. That's one of the nice things about Swampland. It's very, there's a lot of things to work on. Any other questions?
Can
Thanks.
you also add charges to make the cobordism trivial?
That's a great question. So you cannot kill this particular cobordism class with particles, because the cobordism classes involve geometry. So whatever you do to kill that charge has to involve geometry as well. This is why the object that kills this charge is involving geometry. Now, this geometry itself could carry some charges, and that's something. There's a technicality of this analysis that I didn't describe, but you're completely right. You need to worry about it, and you need to carefully quantify it. The bottom line is it doesn't impede the argument, but absolutely they can carry charges. But in any case, to kill cobordism charges, you need geometry on top of just charges under some other fields. Did I answer your question?
Yes. Yeah.
Okay.
Thanks.
Any other questions? Okay, good.
Sorry, but so this T3 over Z2 is not just a point as you have drawn there.
That's right. That's right. So yeah.
It's not just a point like a source or
no. What I'm doing here is the following. Okay. So because
you said it has some geometry.
That's
so
right.
It's not a okay.
This thing is a point. Okay. The thing that I conclude exists from cobordism conjecture is a point, or rather something localized. You could say something localized. Once it's something localized, I am allowed to use it as an ingredient in string compactifications. So once I know this thing exists, I know this other thing exists as well, because this other thing is like a torus quotiented by this Z2, looks locally, is like 8 copies of this singularity glued together. Okay. So what is T3 mod Z2? It's just take R3, but identify coordinates like this. So when you look at this action, you look at fixed points, you need to solve equations like x equals minus x, for instance, y equals minus y, z equals minus z, which is a fixed point. So first, of course, this has a solution, which is x, y, z equals 0. But since the coordinates are defined modulo 1, saying that x equals to minus x plus 1 is also a valid solution, okay? Because they are identified on the torus. So that gives you another fixed point, x equals to 1/2. So when you play this game, you find that it's a total of 8 fixed points, whose coordinates are a, b, z, where either a, b, c are either 0 or 1/2, okay? And correspond to the 8 fixed points that I was drawing here. And locally, just look at it locally. If you zoom in on any of these fixed points, they all look like this. Globally, they are glued together in this way. But the gluing of it is just what we usually do in quantum gravity. You can just, if you have one singularity which is good, you can glue it to another, and that's fine. That's all we do.
Okay.
Right. Any more questions? Very good. So let me then change gears. As I said, I'm going to tell you now about something which is more speculative, but also more relevant for observations. And it's not going to be based, everything I describe in this lecture, all these recent developments. I was asked to give a lecture on recent developments of the Swampland program, and most of the recent developments that I've been telling you about have been happening about no global symmetries conjecture, around the no global symmetries conjecture. But this one I'm going to be telling you about is not about the no global symmetries, it's about the weak gravity conjecture. I believe you heard about weak gravity from Miguel in the second day of the talk. So I'm going to be recapitulating a little bit what weak gravity is about very, very quickly. Okay. So what is weak gravity conjecture? Weak gravity conjecture tells you that in quantum gravity with, let's say, a U1 gauge field, there is a particle such that its mass, it's lower than its charge. So it's the gauge coupling. This is the charge, integer charge, in Planck units. Okay, so that's with gravity. And there's a lot of evidence for it, which I'm sure Rene gave you, coming from string compactifications and a bunch of other perspectives. I'm not sure that she told you what is the heuristic reason why we believe weak gravity works, which is that maybe she did, but I'm not sure. So I'm gonna briefly review it. Is we believe so weak gravity exists so that black holes decay without becoming super extreme. What does that mean? Well, here's the charged black hole metric, Reisner-Nordstrom metric. Okay, so it's of the form minus f dt squared plus dr squared f plus r squared d omega squared for f equals to 1 minus, I'm working in units with, I'm going to set Planck equals to 1, okay, for the rest. So I'm Planck equals to 1. 2 over r plus g squared q squared or r squared. So that's the solution. Okay, so that's a black hole metric. This is the charge black hole metric. We can find the horizons at f equals 0. So f equals 0 is a quadratic equation which has two solutions. You can check are m plus minus m squared minus q g squared. Okay. So these two are the inner black hole horizon and the outer black hole horizon. You can see that whenever m is bigger than GQ, there's two solutions. And if m is lower than GQ, there's no solutions. What that means is that when n is lower than q, what you're describing is not really a black hole, is not a black hole at all, it has no horizon, is what we call the naked singularity. And naked singularities are generally badly regarded. There's a conjecture that they don't exist in general relativity, which is called the cosmic censorship conjecture. But really, I mean, conjectures based on just general relativity could either be wrong or right. You never know. There could be naked singularities there just lying for some reason. Really, the convincing thing is that we never have naked singularities in string theory. Okay, In string theory, you can have situations where there's very strong curvatures, which are localized and they don't have a horizon, like the orbifold singularity I was describing before, but they are never parametrically large. Okay, these curvatures are always of string size, and you cannot make it much larger than string size. You cannot make a very, very large object with arbitrarily high curvatures ever in string theory. So I take this principle to be good, to be a good principle about quantum gravity. And what that means is that if I, for instance, draw a mass versus charged plane, as I drew here, and I draw here, this is the line m equals GQ. Then if I have a black hole, then it has to be here on this side. Black holes can be on this side of the diagram. Oops. I was supposed to be able to move this thing, but it doesn't. Anyway, so black holes are usually on this side of the diagram. You would not be able to have a black hole solutions here because this is where the naked singularities are. So one argument for weak gravity is that, well, black holes evaporate. So how do they evaporate? Well, black holes evaporate and they lose mass by doing so, and they lose charge. Mass, they can lose from Hawking radiation. Charge, they lose because they have an electric field and the subversion of the Stringer effect in the near horizon geometry that allows us to lose charge. So a black hole is going to start moving like this, perhaps something like that. Ideally, we want the black hole to completely evaporate back to empty space. What we don't want that happens is that there's some process such that the black hole does like this, because it would become an unwanted naked singularity. Okay, so one can check that the kinematic condition that a black hole doesn't do this, that it evaporates while remaining subextremal, is weak-gravity conjecture. So let me do it quickly because it's really a simple argument which is in the original weak-gravity paper. Suppose you have a black hole with charge q and mass m, and it evaporates a little bit by emitting a black hole with charges q prime, m prime, and a little particle with charges q, n. Okay, so of course by charge conservation we have that q prime is q minus m, and by kinematics of it, if you ignore momentum, the mass of the final black hole has to be lower than the mass of the initial black hole minus the mass of the particle. Okay. I'm, by the way, here I'm setting just for so I don't have to keep on writing G all the time. I'm putting G equals 1 momentarily, and I will restore it later. You can carry G if you like. So if you have this thing, okay, then what we want to impose is that the charge to mass ratio of any black hole is below 1. That means that the black hole is in this region. That means that the black hole is in this region. Okay, so it's subextremal. So we want that if we impose that the original black hole has Q Q lower than m, and we impose that the final black hole also has Q bigger than m, we want to see what constraint that means for the charged particles. And well, we can just substitute and we get Q minus Q over m minus m. And you can rearrange, that means m minus m, q minus q. Okay, now this is a constraint on m and q, which becomes strongest when m is equal to q. And I can look at a black hole which has m equal to q, it's just a black hole on this line. So when m is equal to q, the two things drop out, and what you get is that if you want the black hole to remain subextremal, you must have m is lower than q, which, if you allow me to restore m blank at the gauge coupling as I was doing before, is precisely the weak-gravity conjecture. So weak-gravity conjecture is about extremal black holes evaporating without becoming super extreme. If you have a weak gravity particle, you ensure that the black hole evaporates like this, and you avoid the bad decay channels like that. Okay, so that was just a very quick review of weak gravity conjecture. Are there any questions about this and about this motivation for weak gravity conjecture? Okay, yeah, this is mostly material which was covered, I think, in Irene's lectures, and yeah, so it's okay. So very good, very nice. The only thing I want to do now, I told you this last lecture, it's almost 8 or 9 in Tehran, so it's more than 8. It's almost 8:30. So you guys are tired. Sorry?
20 past 20.
20 past 20. Okay, so it's late. You guys are tired. So what I'm going to be doing is very simple. It's really simple. There's going to be no equations, just drawings. And we're going to get a lot out of very simple things. So the only thing I want to do, repeat above argument for black holes in the Sitter space. Black holes in the space-times where the cosmological constant lambda is bigger than 0. That's all I want to do. Okay, so you've been hearing a lot about the Sitter space in large lectures and also in Thomas's lectures. So it's unclear how to do the Sitter string theory, but we live in something which is approximate the Sitter. So something like the Sitter must exist in string theory, and this is why one should care about what weak gravity predicts for black holes in the Sitter. Well, so what does happen? Well, it's very simple modification. So the metric, which was this thing before, right, just gets a correction. Okay, just gets a correction like that. So we can just repeat the same argument, do the same thing, taking this correction into account. It's a very simple exercise. So let me do it. I'm gonna draw this time bigger I'm gonna draw the lines here. Oh, and I think I can, yeah, perfect. Okay, so here's the mass versus charge. And now I need to find out what's the extremality condition. The extremality condition is when the inner and outer black hole horizons coincide. And the equation F = 0 is now quartic. So the locations of the roots are controlled by a complicated function of M and Q, which is called the discriminant, which I won't write out explicitly because it's not very helpful. I'm just gonna draw for you, okay? What is the allowed region? Okay, so let me draw it. I'm gonna draw it in blue. So, okay, actually, let me first draw in green the original extremality line that you have from flat space. So let me now draw it for when you take into account the curvature. So what happens is, okay, fine, maybe there's some correction. That's not very surprising. So it does like this. So it goes up. Okay, so of course you were expecting a correction. No big deal, no surprising. The surprising thing comes now. It does like this, and then it does like this. And then, I don't know about you, but the first time I learned about this, I was very, very confused. What does this mean? What am I saying? What I'm saying is that good black holes, like actual black hole solutions, only exist in a bounded region in the QM plane, okay? So what I'm saying is that for instance, any value of the charge that you pick, this value of the charge, any value of the charge that you pick, there is both a minimal radius for a black hole, minimal mass, which of course you expected. There's also maximal mass, maximal radius for the black hole in the Sitter. What is going on? Well, maybe you guys remember that from Lars's lectures. I'm sure Lars talked a lot about the fact that de Sitter has a horizon. So if you're an observer, there is a horizon far away from you, 1 Hubble length away, and things beyond that horizon are expanding faster than light, and they cannot reach. That means that any sensible physics you have must happen, that you can access to, must happen within the static patch, within the Hubble horizon. And so in particular, if you have a black hole at the center of the horizon, it can be small or it can be bigger, or at most, it can be as big as the horizon. So this is the effect that we are seeing here. There's black holes as big as horizon, as the de Sitter horizon. We are talking, the guys here are the biggest black holes one can ever find in the de Sitter space. They are called Nadii solutions because of the person who discovered them in the 40s. And so that's the biggest black hole that you can have in the static patch. The fact that you have a horizon completely changes the physics of black holes and gives them a maximal size. Okay, so what about this? Well, one needs to study evaporation of black holes, and I want a black hole that does like this, as I said before, just like we did for weak gravity. If you do it for black holes which are here, start here or here, and you ask how they evaporate like this, there's no problem. You can compute it explicitly. But interestingly, if you start with a black hole which evaporates like this, it may evaporate like this. So something nice, it does something like this, depending on your particle spectrum. But for some choices of particle spectrum, it can actually evaporate. I'm going to draw this in red because it's wrong. Sometimes it'll evaporate like this. Okay? So the red thing happens if charged particles are too light. So one can compute this very precisely using the Schwinger current and whatever, but if particles are too light, the black hole can discharge, if there's charged particles which are very light, the black hole will emit its charge much quicker than it emits mass, and so it will leave the allowed region. Now, once a black hole gets to this region, it is really not that different from, this can be smoothly deformed from the naked singularities that we were talking about before. So it's a bad region. And so we want to impose, we think that if black holes, super extreme black holes are not allowed, if we extrapolate the principle of weak gravity to the de Sitter space, okay, we get a condition, a lower bound on the masses of charged particles, which I am going to write down for you. Because it's a bit late, I'm not gonna explain the derivation, but basically the bound that one gets is that the mass of every charged particle has to be bigger and similar than G times m Planck times h. Okay, so this bound is a new Swampland condition that you get out of applying gravity to the de Sitter space. So this is for every charged particle, and it's what we call the Festina-Lenti bound. So this is coming from a paper by, this is studied in 2 papers mostly. People are starting to study also other implications of the bound, but it's coming from 2 papers I'm going to write down for you. So the first one is 1910 01648. This is by myself, by Thomas van Riet, who was also lecturing in the school, and by Gerben Benken. And the second one, where we actually study very interesting phenomenological implications, is by myself, Thomas van Riet, Gerben Benken, and Kombun Bafa. Okay, so this bound, okay, has less support than the other Swampland bounds, but it has very strong implications. For instance, this thing here is the Hubble scale. So that m Planck squared h squared is equal to the cosmological constant. So you can actually rewrite the bound as like this. You can say that you can write it as an upper bound on lambda where you can put an upper bound on cosmological constant depending on the spectrum of charged states. So now we can apply this to the real world, and we can substitute here the electron mass, which is 0.5 MeV. And then the bound that we get is that lambda has to be lower than 10 to the minus 88 m Planck to the fourth, which you need to compare to the experimental value. And explaining why this value is so small is one of the big open problems in physics, which is this. Now, it's still 30 orders of magnitude away, but it breached 90 orders of magnitude from a value further one, which I think is doing a good job. There's other things that you can say with this Festina-Lente bound, because for instance, when you apply to non-abelian gauge fields, it's telling you that because they have gluons, and gluons are massless charged particles, they violate the bound. So non-abelian gauge fields are not okay with the Festina-Lente bound in the sitter. So Festina-Lente is really predicting there cannot be exactly massless long-range non-abelian gauge fields in the sitter. And this is satisfied in the real world because the SU3 that we have is confined at lambda QCD, roughly 150 MeV. And the SU2 fields are Higgs. So at around 80 GeV. So there's no way that you can find so it doesn't happen that you find non-abelian long range gauge fields in the real world. So that's how the real world is compatible with Festina-Lente. You can also use it to give bounds on the Higgs potential. For instance, if I just draw the Higgs potential in the usual Mexican hat shape. Okay, that was, yeah. So that we live here. LHC has only measured things around here. It has not measured this region. So somebody could come and try and replace the Higgs potential. This is a model that would not be in contradiction with experiments. It's trying to replace the Mexican hat that we have here by a cowboy hat, like someone from the United States likes cowboys, and replace it by a cowboy hat. Could replace by cowboy hat. So you have a minimum here. Well, this minimum is very much constrained by Festina-Lente to the point that when you apply Festina-Lente to this scenario, this one is still okay. This one you rule out. So Festina-Lente is not very pro-American when the Higgs potential comes into consideration. And just to wrap up, there's many interesting things that you can do with Festina-Lente. It has constraints also on inflation and on, here it is, and it also constrains models of dark matter. One often assumes that there's a dark matter, that the dark matter particle has it has some particle which is charged under a dark U1, so a long-range gauge field like our own, but different. And when this happens, this particle can mix with our electromagnetic U1, leading to what we call Milli charges. So what can happen is that this particle, this dark matter particle, gets a small electric charge, and people are actually looking for this in experiments. Using Festina Lente, you can get bounds like this. Okay, so here I'm putting a figure of some upcoming work, but you can constrain, you can relate the mass, you can relate the mass of the Milli charge of matter particle to its Milli charge, to the small electric charge. And the bounds that you can get from Festina Lente, which are drawn by the green and gray lines here, are compatible, are constraining regions of parameter space that are going to be probed in the near future by experiments, which I think is quite exciting. So I just wanted to end the lectures with this general Festina Lente bound. Is more speculative. I cannot, I've spent a lot of time telling you how the Swampland constraints become true in string theory and giving you general arguments for them. I cannot do any of those for Festina Lente simply because, as you have been hearing in these lectures, it's very difficult to obtain the sitter or quasi the sitter in string theory. But it's a natural extrapolation of the Whig-Wright principles in flat space. And so we believe, at least I believe, it's possibly true. And I am very excited about working out all the consequences that these bounds can have. And there's lots to do. So with this, I will take questions about Festina Lente very soon. But before I do that, let me just, since I am the last person to speak in the school, I have the honor to wrap everything up for everybody. So with this, I think we reached the end of our short hike, at least the part I guided you through the Swampland. We focus on some cutting-edge developments. But it's a field which is young, rapidly evolving. There's many opportunities to work, many open questions, and it's super exciting because we are really trying to find universal effects that quantum gravity has at low energies. And I cannot think of a more exciting research question. And on top of that, I am a person who loves particle physics phenomenology, loves mathematics, loves string theory. I love learning new things in many different fields. Swampland is perfect if you're like me, because it forces you to learn all of those. You've been hearing from 4 different lectures in this school, and I haven't attended the lectures, but I assume they were very different to each other because there's many angles to Swampland, and there's a lot that you can learn from that. And I think it's very exciting on both because of this and because of this. It's very nice. And with this, I'll just like to close the lectures with a big thank you to all of you for listening, for the great questions that I got, and especially to Hesamadin, Amin, and Mari for putting this together and making it possible. So I will take questions now, but before that, let's give a big applause to Madi, Hesamadin, and Amin. Thanks very much.
Thank you. Thank you for this very nice lecture and the other 3 interesting lectures. Thank you very much for accepting our invitation. So we have time for questions. And by the way, thank you, audience, for holding up this late. Thank you.
Yeah, thanks very much. I really appreciate that. Thank you very much.
Yes,
Yeah, Amina, you have a question?
Yes, so if I understand correctly, for Festina Lente to hold, the Sider vacuum must be sufficiently long-lived, right?
That is what, yes.
Then would some sort of chain-like inflations with several minima avoid this Festina Lente bond and the constraints it imposes on the standard model?
Okay, so Festina Lente, for it to hold, it's true that it only applies in quasi-static solutions, and it also depends on the gauge coupling. We have a precise condition involving the gauge coupling and the potential, and actually that's a bit of string theory, indirect string theory evidence for Festina Lente, because we found some conditions that the binary black holes do not hold, do not exist, so you cannot run the Festina Lente argument. And actually, this condition is violated in the string theory examples, which violate Festina Lente. So we have not counter examples to Festina Lente coming from string theory. Now, for the standard model, however, what we measure for sure is that V prime over V is small enough that Festina Lente holds. So I don't think that you can avoid the constraints for Festina Lente in the standard model. During inflation, you might think that you're able to evade them because inflation only lasts for 60 EFOLs, okay? Or equivalent, you could also think, for instance, something like this is true. Maybe our own vacuum only survives for a very short time, and so you do not apply festina lente. But it's very interesting. So we worked this out in the second paper, and we're gonna discuss it a bit more in this paper that I imposed. So the constraint that there are no. Okay, so festina lente happens because black holes evaporate very quickly. Okay, so if you want the black hole to, for instance, last 6 TFLs of inflation or 1 TCC time or something like that, you need to suppress the evaporation of the black hole is very quick. Okay, it's much quicker than Hubble scale. So the way you can suppress this effect is by making the coupling very, very small. But if and you can actually compute how small the gauge coupling would have to be, which we did. And the gauge coupling for this to work has to be smaller than h over m Planck, okay, squared. That's how small it has to be for you to avoid festina lente. Now, there is something that I didn't describe in these lectures. There's a magnetic, in the same way that weak gravity conjecture has electric and magnetic versions, there's a magnetic version of festina lente, which actually we didn't work out. And me calling it magnetic version of festina lente is a bit anachronistic. It was worked out in the 2006 paper. And in this 2006 paper, they find that the condition that they get from magnetic version of festina lente is precisely the it's the opposite of this. So the condition you need such that festina lente doesn't apply will force a gauge coupling which is so small that is incompatible with magnetic festina lente. So it always applies in the end. It applies in our universe if it's gonna die in 1 Hubble time because of TCC, and it certainly also applies during inflation. So you really need to take this constraint into account. There's no way out, no simple way out just because the universe has finite lifetime. I hope I answered your question.
So what if there are so many successive minima during inflation, so that the de Sitter space decays to the other minimum, to the next minimum before the black hole evaporates?
Good. So you're thinking, let me see, you're thinking a situation where the potential is kind of like this, something like that?
Yes.
Very good. Very, very good. Okay, so when you have a potential like that, we have a paper with Irene Valenzuela, Alec Bedroya, and Kun Ru, in which we study this situation. When you have so many successive small tunnelings, you can replace this by an effective potential, which is like this. Okay, all the successive tunnelings don't change the universe too much, and you can replace by effective potential, which is like this. And this effective potential is the one that matters for festina lente. So, for instance, if V prime over B is bigger than order 1 number, okay, then you do not apply festina lente. You do not apply, you're right, then festina lente doesn't apply simply because you don't have narrow black holes. But a situation like this is not the present, the present, it doesn't describe accurately our present vacuum, okay? So for our vacuum, if you have a situation like this, like the one we're describing here, the tunneling time between one vacuum and the next, combined with the steps, is such that the effective potential has very small V prime over V, because that's what we measured. And so this situation happens, but it's not describing our world. And during inflation is more or less the same. The whole point of inflation is that V prime over V, the effective V prime over V during inflation, is very, very small. So it also does not apply during inflation. There are other circumstances which are as you described, but do not describe either inflation or the standard model today.
Right. Thank you.
Thanks for the question. Any more questions? I don't know about you guys. If I was you, I would just be wishing to go to dinner.
It is interesting that the festina lente bound is the only one that that doesn't get trivial in the decoupling limits.
Very good point. Very good point. But you see, this is very related to the fact that it's a conjecture about de Sitter. So when I write something like this, okay, what you're saying is, well, if I say M Planck to infinity, the right hand side goes to infinity, and so it doesn't decouple, right? It's not like
it goes to 0 even faster. Exactly.
The point is that we don't know what happens in quantum gravity. It could be that all consistent family of de Sitter has h going to 0 as M Planck goes to infinity, right? So we really don't. It's really about the sitter, and the conjecture has this weird feature because the sitter is weird.
Interesting.
Mhm.
Reza, another question.
Yeah, there's a question by Rita. Yeah.
Thank you for your very nice set of lectures first.
Thank you for all your questions. You ask a lot. Thanks a lot.
Thank you. I had a question which is not directly related to your, may not be directly related to your talks, but if the effective four-dimensional scenarios like brain board scenarios like that of Erkani, Hamed et al. And
Yes, you mean like large
Randall,
extra
Sandler,
dimensions or random? Okay.
Are they fitted within the landscape or
the Swampland?
to
Very
what extent they can be counted to be in the landscape?
I think that's a great question. So for instance, so you're asking, let me go over here. So you're asking, if I understood you correctly, you're asking about two kinds of scenarios. So the large extra dimensions, which is called the Hamed, the Valley, Dimopoulos, right, scenario. And you're also asking about Randall syndrome. Okay. So yes. For large extra dimensions, I think it doesn't contradict anything about Swampland program that we know. For instance, one way to realize large extra dimensions explicit in string theory, I can take M theory on a compactifying Calabi-Yau threefold. So M theory has 11 dimensions. So when compactifying Calabi-Yau threefold, you have 11 minus 6, 5 dimensions theory. And just like I described in my lecture about covariatisms, you can take one of these dimensions and compactify on an interval. Okay? And so you end up with a configuration like this. You have some Calabi-Yau, which is very small, and an interval, and you go from 5 to 4 dimensions. So this is very much like the large extra dimension scenario with one extra dimension, and you can do it also with higher dimensions. So large extra dimension, I think, is easy to embed in string theory. Randall syndrome, possibly you can also embed in string theory, but it's more difficult. Why? Well, what I drew here also looks promising for Randall syndrome. It looks like the IR brain and UB brain, right? But some of the properties are a bit different. So for instance, Randall, so in string theory, let me just draw the interval in string theory and this interval in Randall syndrome. So in string theory, these two brains have tension equals 0. And the lambda here is equal to 0 too, okay? And for Randall syndrome, the whole point of the warping that you get and so on and so forth, one tension, there's two different brains. The tension here is bigger than 0, and the tension here, tension 1 is bigger than 0, and tension 2 is lower than 0. Now, we have brains with negative tension in string theory, like orientifold, so this is not a problem in itself, but there's a few of them, there's not that many. And you also need to get the lambda lower than 0 here in Randall syndrome scenario. So all of these ingredients, I don't see any obvious reason why they're in the Swampland, but it's also true that it's not super easy to get them from a string compactification. Okay, so right now I wouldn't say there's any obvious contradiction with any Swampland principle that I can think of, but there's also not a very concrete invariant in string theory, which puts it in a bit in a gray area. Using the color code I was having before, for the rank 8 theories, I would color this as yellow. We don't know. We don't know if this is in the Swampland or not. Did I answer your question?
Yes. Thank you.
And thank you for all your questions.
Thank you so much. Another more question. Ask more question. Yes. I wanted to know about this cutoff lambda, which is of the order of G coupling times M Planck. Is that the same thing as the unification scale of gravity?
Cutoff lambda
gauge.
Sorry. Okay, so you're asking about weak gravity conjecture. So you're asking for lambda. So what I was calling lambda in this lecture was the cosmological constant, but you're asking about the magnetic weak gravity cutoff which is G times M Planck, correct?
Yes, yes.
Okay, so
Is this cutoff the same thing as the unification scale of gravity and gauge fields? Is different?
It's different. In many cases, it can be different. Okay. So for instance, let me. Okay, so that by the unification scale of gravity and gauge fields, one could mean the scale at which the two of them have the same strength, sort of, right?
Yes.
And this cutoff is not the same. I think Irene might have talked about the difference between this can be the EFT cutoff. It's the scale at which, so you start with a theory in D dimensions and you have a quantum field theory description. At this scale, that breaks down. But it's not the end of the world. It may be that you have a D+1 or D plus K dimensional QFT description. Okay? And it doesn't mean that it doesn't mean that you cannot describe this quantum field theory. So an example of this, for instance, is when you get like a theory, let's say 5D theory of gravity, and we put it in a circle. Okay, so when we put it in a circle, there is a 4D Kaluza-Klein photon with gauge coupling related to the square root of the radius of the circle. Okay, and so there's a magnetic gravity cutoff like this, lambda G times M Planck, which comes out to be, in this example, the Kaluza-Klein scale. The scale, this is not the scale at which gravity and the Kaluza-Klein photon become equally strong. The scale of equality of unification, it's a higher scale, which Irene introduced, I think, which is called the species scale, which in this setup is the 5-dimensional M Planck. Okay, that's the energy scale where the photon and the Kaluza-Klein photon and the rest of gravity unify. And if you want to write it out in terms of 4-dimensional data, lambda species is G to the 1/3 M Planck in this example. So because G is small, this is a much higher scale than the one that we have here. So this is much lower than this. Okay, so it's at a higher scale.
So the cutoff is much smaller than the unification scale. You're saying the cutoff lambda is much smaller than the unification.
That's right. That's right. So at this cutoff is the scale when you start seeing like extra particles. Okay, you start seeing extra particles coming in loops. So you start seeing a tower of particles, but they're still there. But still, the forces of these particles, electromagnetic forces, are stronger than gravitational forces. And it's only when you get to this higher scale that I'm describing that the two of them become equally strongly coupled.
Thank you very much.
Thank you.
Goodbye.
Bye.
Any other question?